We're in it. Spetri. Oh, you're about to hit 40. It's pretty hype. All right, another reading group. Still working on chapter 7 on induction. Why are you still 17? Yeah, I guess you need to get some more first. I don't know. Pop it in Discord. Yes, but you really should have let Eldritch have that. You got two more? I thought you were. I'd have to look at. I don't remember what this. Oh, God. I don't remember. I'm sorry, Eldritch. Hey, Bode. How's it going? I'm doing good. Hey, Nand. I'm good. How's it going for you and Nand? Okay. Um, who chairs? Yeah. Um, I'm just looking. What? I feel like the last time we did the group, we skipped around. Like we skipped ahead. I wanna. What did we do in the last group? Hey, $10. Um. Okay, we did 11. That's the one that we skipped ahead and did. You don't have a new solo joke aside because I'm lazy and tired. No worries, Eldritch. You did your duty by dropping them in Zach's chat. Good, that's good to hear, Anand. For the reading group, I'm focusing on questions from this textbook, but if you're willing to wait until maybe like the 2 hour-ish mark when this thing is over, I'm happy to take a look at it. And I should also make the disclaimer that I might not know the answer to your magnetism question because I'm basically just learning this for the first time. So I'm not very good with it and I don't know everything in the first place. Okay, the next one I have in the order here is I got a bunch of like there's a 2-star problem and then a 1-star problem. They seem like they kind of build on each other. I think so. Then another 1-star problem after that. So I'm going to drag in this first one with 2-star. And we haven't done a... I don't think we did one on this mutual inductance coefficient. Finlux, are you hopping in today or are you just gonna chill? Either way is fine, but... Oh, there you are.
Hey,
Hey. How's your Saturday going?
it's going pretty good.
Nice, nice.
I should have read some physics, but I was hanging out in Zach's stream.
No worries. I was like just like lurking, trying to do some other things, but then when he went to that coding one, I was like, okay, it's a little bit too interesting. I have to participate in this.
You know, that was a good question. I think I thought I had an answer to it, but I had to step away, and when I got back, he was done. So,
uh, I didn't read the entire question to be honest. It was something about like given 100 random points, prove that there's always at least one collinear triple or something.
yeah, it was find the minimum K such that there have to be K
Oh, I
open,
see.
something like that.
Empty consecutive triple. The triangle does not. Oh, okay. Yeah, I'll
I
actually go
thought
through
I
and
think
read the question at some point because that's weird. Sorry, what?
I thought I had a good idea about it.
Hmm.
Like, tell me if this, I don't want to derail the physics, but
Oh
tell me
no.
if this seems like a good idea. Let's say I started with this point. Let's call that point 100. Then I could go to like 0.99 here. Well, I wanted these to be close together, actually. Let's say this is 99. Let's say that's 98. Oops, what happened? I lost my escalibur. Oops.
Oh, there's two of you in here now.
Oh, is there?
Yeah, that's funny.
Okay, so look at that. Now I can go to 97 right here. 96 over here.
Oh yeah, you're talking about like
95.
spiral.
Yeah, 94. Now I want to claim that, because the only problem with this is that I have to make sure no 3 points are ever collinear as I do this, right?
Mm-hmm.
Now, doesn't it feel like, because I have the whole plane to move around in, doesn't it feel like I have enough freedom? Like, let's say, so now I want to put 92 up here somewhere, right? Somewhere up here. I got enough room to wiggle up here that I should be able to make sure that I can find a point to put 94, that it's not going to be collinear with any pair of the other ones that I've already put down, right? I mean, I feel like that's guaranteed. And what's more, I feel like it's guaranteed no matter if I go to 100 points or 1,000 points or a million points. I feel like that has to be, because what have I got so far? Like, let's say I got 10 points. I've got 10 choose two lines that I have to avoid, right? But, I got so much room to move. I can just keep going around out like this, and I feel like I can always put another point down that's not collinear with any pair
Like
that's
you can
already
always avoid
on the
like
table.
that line there. Like, you always have
That's
enough room to
exactly
avoid that. Yeah.
that's exactly right. Yeah, and I can avoid this line right through 196, and I can avoid 98 to 96, right? And I can avoid all those pairs when I want to put this one down.
Yeah.
And so
So
if I go out and spiral out like this, then thinking about the points the other way as I come in, every triple is going to have a point inside it, except for the last one, these three inside here, the 98, 99, 100. I feel like those three are going to make an open triangle or whatever. But all the other triangles, I can always set them up so that it's got points inside it, just by the way I'm constructing it.
I mean, I remember Mega saying that like, it has to work for any random arrangement of points, but are you saying that you can maybe like make this spiral pattern from a random arrangement, or
Well, if I
you're not allowed to
understand the
like
question
construct these, I
correctly,
thought.
yeah,
Maybe you are.
if I understand the question correctly, they're just saying for any given set of 100 points, right, labeled points, find the maximum K that we can guarantee that we'll have that many uh, open triples or whatever they called it. So what I'm saying is, it's kind of like I'm doing the problem backwards. I'm trying to. Do you remember that problem that we all looked at with the monsters in the grid, and you had the snail was trying to get through the grid? Did you look at that problem, Don?
I don't remember that one, no.
Okay, it's sort of similar to that. It's like you're trying to find some optimal solution where the game is the deck is stacked against you. Like here they're going to give me a collection of 100 points, and I'm trying to find the worst possible setup, that randomness could have given to me.
Oh yeah,
Yeah,
Turbo.
yeah,
Yeah.
Turbo the snail, exactly. Yeah, yeah. The Turbo the snail problem was hard.
I
It was
read
hard.
the first part of it and then I was like, okay, I probably can't do it. That's all I remember it.
The only reason I tried it is because I got a friend who told me that he had a solution to it, and I was like, oh, okay, well, let me think about it. And he said he'd worked it out in just a few minutes, and I was like, man, okay, let me
Wow.
think about it. And it took me like 2 hours to finally come up with the algorithm there.
I have boats that some solved in 30 minutes. Boats solved it in 20. Wow.
Yeah, nice, nice.
Also, sorry, no, this is a problem that we were talking about on Zach's stream. That this morning. It's completely unrelated to physics, what's on the screen.
Yeah, it might
I'm
be a.
interested to
People were
think about it
saying it
more,
might be
though.
a Putnam. It might be a Putnam problem, but I don't know if it is or not.
Oh, okay.
And I didn't copy it down, but I think Zach has it in his Discord somewhere, doesn't he?
Yeah, it's in the forum. Uh, so it's called Combinatorics, posted by Fran.
All right. Well, let me erase
Okay.
this picture I drew. And we'll try
Oh shit, that
some
got the
much
image.
harder problems. Oh, did I
Yeah,
erase it? Sorry.
no
Sorry,
worries.
Don. Can I?
I got it back here.
Nice.
Okay. Um, Easy problem for IMO, but it's luck based. You have to guess the solution correctly. That's the difficulty. Oh no. Okay. Okay, so figure 7.31 shows a solenoid radius A1 and length B1 located inside a longer solenoid of radius A2 and length B2. The total number of turns is N1 on the inner coil, N2 on the outer. Work out an approximate formula for mutual inductance M. Ooh, approximate. Okay, we're gonna have to do some Taylor series stuff, I guess, but okay, I thought I didn't see the word approximate. That kind of scares me, but me. Oh shoot, did you get this far in chapter 7? About like the M constant or like coefficient?
The capital M.
Yeah.
Nah, but I'll wing it.
Okay. Fair enough. So we know that
We're kind of at a point now where I feel like, I read the book or don't read the book. It's not making much difference.
yeah.
I'm kind of treading. I'm not really treading water anymore. It's over my head. Like I said, I'm just here. I'm just here to watch you do it and and try and catch math mistakes if I can.
Okay.
That's the only thing I'm good at.
It's better than nothing.
Yeah.
Oh, okay, bud. Sounds good. Potentially easier induction problems for my E&M class I could give you guys if you want to warm up. I want to at least try this one, but if it proves to be too hard, then I might want to take you up on that.
This does look like a picture from chapter 6, right? When they were doing solenoids.
Yeah. And so we could try to figure out. I mean, it seems natural to me to try to consider the flux from the big solenoid through the small one for calculating phi. How do we know anything about the current? Like, what do we do with that?
To find mutual inductance, don't you just sort of basically trying to work out how the current in one induces a current in the other one, aren't you?
Yeah.
So for example, if I had a battery connected to the outer solenoid, right, and I switched it on, so it goes from zero to I turn the switch, throw the switch, and then that solenoid the current starts to flow through it. I want to find out how that induces a current in the inside one. So I don't think you have to know the currents. So it's like a ratio between them or something.
You're right, yeah. And I was looking at the example problem they did to work out the mutual inductance to the two rings, one inside the other.
Okay.
And so I still wasn't quite sure how we deal with that, like, or like what we do with that I, but it seems like maybe, oh, it just, you just leave it and it cancels out, or at least you could expect it to cancel.
Yeah, because it's some kind of ratio, so I'd think it would cancel something.
So they get the flux by taking the magnetic field due to the big outer ring and multiplying it by the area the smaller ring inside covers. And then you literally just divide an I. And that's your coefficient. So I assume it's going to be a little bit more complicated for these solenoids. But how can we get the magnetic field of a solenoid of finite length? We have one for infinite length, but I don't think that's going to be good enough. Unless we can assume that B2 is much greater than B1, and that's the approximation that we're supposed to make.
Oh.
That would be a convenient one, because I do we even know? Like they give us the field for infinite. In chapter 6, weren't we dealing with another finite solenoid? I thought there was a way to deal with that.
Yeah, I feel like we had a question about that last week,
Or maybe it
but
was last week, yeah.
I don't remember how we dealt with it. Or if we did.
Um, oh yeah, so next of a long solenoid with radius r, length l, and n turns. Oh,
We got that.
so
We
they
got
said it
that
was
one right,
long.
right?
Yeah, so we
Yeah,
just
they
used
said
the
it was
formula for
long.
infinite long. Okay.
Okay.
So I feel like we kind of gotta say that B2 is much greater than B1. Whereas I don't know how else we would do those. But if we can do that, then the field of the bigger one that I call B2 is going to be mu naught N2 I over its length B2. I wonder if we need to talk about the radii, but I hope not. So then I think the flux through the smaller one is going to be this field. Is it that one? No, it's that one. Flux is field times area, right? So mu naught into I over B2 times pi A1 squared. And so that would just mean that M is that same thing, but without the I. I don't know if this is right, but this is an answer. I'm also writing this sloppily. Una
Seems too
pi.
easy, right?
Yeah, it does. We could theoretically try to do the opposite direction and see if we get the same thing, because they should be the same thing.
Yeah, you're saying instead of going from bigger to smaller, go back from smaller to bigger?
Yeah, we would have. I guess we have to do the same approximation that B2 is much bigger than B1.
Hmm.
Um, I could see it working out similarly because if the flux just goes out in a straight line, it's only going to make still a circle of radius A1, like out the end of the big solenoid. Like it's not like the field from the smaller one is going to go way out there or something.
Yeah, but once you get away from the inside of the solenoid, don't the field lines start to curve?
Oh, you're right. I guess I could draw it like really close. But it's not. Well, yeah, I think that's okay. Although I think this calculation of the magnetic field would be different. Like we'd have N1 over B1. And I wonder if I shouldn't be taking these as the same I, because one of the eyes is just whatever current we're running through the big solenoid. The other current is whatever is induced in the small one.
Hmm.
Maybe. Calculate the flux of B2 through solenoid 1 because of what Fembach said. Okay, so but we like you should be able to do the opposite direction though, right? Because at least that's what we did do, like right over here, the big one through the small one, like the flux of the big one through the small one. But this just felt a little bit too simple, so I was looking for a way to verify that. Well, yeah, I want to use the fact that they're equal to just check this answer. That's why I was considering the opposite direction. Because of the edge effects of the field. Oh, okay. It's just too complicated to go the other way. Hmm. So this answer doesn't depend on the number of turns in the small one. It doesn't depend on the radius of the big one. That doesn't seem right, but like I don't know where they would come from, those factors. So in principle, it's possible with an SC integral. Okay. That nice formula doesn't apply here. Okay, fair enough. I don't know. I don't know what to do here, so I might like maybe we check the answer.
Okay. I mean,
Because I think this.
I'm not confident, but
Yeah, me
I don't
neither.
know why. I don't know.
It does have the same dimensions as an answer they get in the example problem with like mu naught length squared divided by length. So that if we ignore the n being the number of turns for length, oh, I don't know if we should ignore that. Oh, no, n is just the number of turns. I think we do ignore that. I don't know. This was number 9. Okay. Current I2 flow in the outer solenoid means it is approximately uniform in the region occupied by the inner solenoid. Value is roughly half, or is roughly that of an infinite solenoid. Okay, yeah, so that is we did make the right approximation.
We're missing an n. The product of the numbers of turns.
The flux. Oh, I forgot. It's the same mistake we made in the other problem. It's
Really?
not
I
the
don't even
flux through
remember.
one single circle of the solenoid. It's the flux through the entire, like every turn of the solenoid.
Oh, yeah, we did. That's right. We did do that.
Ah, okay. So we need
Oh, so you
another.
found it through like one loop. Is that what it was?
Yeah,
Oh.
we need an N1 out there. The spaghetti code. Thank you for the follow. Dang it.
Well,
Okay.
that's not bad. It was so close.
Don't worry, I never made the same mistake 3 times in a row.
Yeah. Third time's the charm, right?
So N1 pi a squared B2. And for B2, we do have the same thing, except I dropped the subscript on the I. Okay, so other than that, I think the answer here matches. Okay, so I think and that's just like the answer to the question. They go on to talk about a better approximation, but that's a bonus, I think. Oh wow, this is a long answer. When obtaining a better approximation for m, we can use equation 6.56. What is 6.56? Oh, you use this integral, but you change the bounds.
Yeah, this is the picture I was thinking of when I said that picture in chapter 6.
Okay. So we could work out. Okay, that's not so bad to work out the field of a finite solenoid. Okay. So then what do they do? Cosine arctan A2 over B2 over 2 equals B2 over root B2 squared plus 4. Okay, sure. It's still not exact because the inner solenoid extends over a non-zero volume in which the field varies somewhat. Okay. For the proportion shown in the figure, the approximation will be pretty good.
So that would bring A2 into the answer.
Okay. And if you take B2 much greater than A2, really? If the length is much bigger than the radius. Oh, okay.
Because that's kind of what we were assuming, right? Was B2 was really big.
Yeah, I guess I was comparing it
Well,
with the wrong value, but so, some very big B2, I guess. Oh, hey, and they're addressing my question of trying to do the reverse.
yeah, and then they say a more accurate approximation is to say that it leaks out immediately after it exits the inner solenoid, which I think is what you were trying to do, right? Like taking a circle right next to that smaller one inside.
Um,
That's that
where,
next paragraph.
oh, it's the next paragraph. Okay. Leaks out this through the side and say it leaks out immediately after it exits the inner solenoid. Okay. Number of turns in the outer cylinder that exists within the span of B1. Okay.
I like the way you did it, the first way.
Yeah. That turned out to be really complicated to do the small one to the big one. All right. Well,
That's probably why they gave it 2 stars instead of 1 star, because of all that extra stuff at the end.
I guess so. Yeah, because otherwise that feels like a 1 star. Um, the next ones that I have queued up are some actual 1 stars, though. What was that one again? 7. Wait, 7. Oh, 9. Oops, 9. We already did 11. So then 12. Okay. Two identical solenoids are connected end to end to make a solenoid of twice the length. By what factor is the self-inductance increased? The answer clearly follows from the formula for a solenoid's L. You should also explain in words why the factor is what it is. Hey, Rapture.
I think I know the answer to this, but I don't know. I think I only know it from a electrical circuits point of view.
Um, I mean, that's not a bad explanation either. This one, okay, number 11 that we did last week is where we calculated the self-inductance due to a solenoid.
Okay.
Is that just an R or is that?
Oh, that's right. And we had to bring the n squared, didn't we?
Yeah.
Yeah, Dr. Cook, exactly. And that's what I'm thinking. I'm thinking of series and parallel, right? That's inductors in series and inductors in parallel.
Yeah, they had a question exactly like that for how inductors add. I don't think I added it because I don't remember why not, but they do have a question like addressing that bit.
We did one very similar for capacitors, I remember.
Yeah, we did. Maybe we might have done the resistors one too.
Yeah, probably.
Rapture, thank you so much for the gifted sub. I really appreciate that. Yeah, thank you. Okay, so I think this is what we got for the self-inductance due to a solenoid.
Okay.
So connected to end-to-end to make a solenoid twice the length, what factor is the self-inductance increased? I guess it's like connecting them in series. That's where you're going with the circuits way.
Yeah.
I mean, I isn't the inductance going down if we double the length? Like, would we just put a 2 in the denominator? That shouldn't be it. I don't know what inductance actually is.
Well,
Does that
okay.
make sense?
If it's the same, if it's sort of the same exact inductor, you double the length, but you double the number of turns. When you, I mean, if you make it twice as long.
Oh, okay. Yeah, if the density is the same.
Yeah, if
Or
the
yeah,
the
it's
winding
probably not the
ratio or
right word, but
whatever.
yeah. Uh, 2n squared. Okay, so that's how we end up with a doubling of the inductance.
Yeah, that's what I wanted to see, double.
Okay.
Because to answer Dr. Cook's question from chat, when you have inductors in series, they add like resistors. So if you have two inductances in a circuit and you put them in series, you just add the inductances to get the sort of equivalent inductance. N over L, turn density.
Oh, okay. Um, I mean, I think it's if we're trying to avoid the circuit's reasoning, like to answer the second part of part A, like if you just double, like we're basically doubling the number of turns that the flux is going through. And I assume that's why we're getting a factor of 2. Parallel inductors add like parallel resistors. Okay.
Yeah. That might be question B, is it?
Uh,
Oh, is it?
current
Maybe not.
flows right on top of each other.
Imagine that one is slightly wider and surrounds the other, so kind of inside the other one.
Yeah, I'm confused on what they mean. Is it like if one of them is like that, you have a slightly smaller one on like above it? Or is it actually, are they actually inside of each other like in the last problem?
I think it's inside it because it says surround, one surrounds the other.
But they say right on top of one another.
Yeah.
Hmm. Around it, so they are in like one is inside the other. Remember that funky differential equation trick of factoring I did? Oh yeah, I think so, syntax. Um, so instead of stacking them on top of each other vertically and they're the same size, we take these two solenoids and put one inside the other.
Does that count as having the same length but twice the number of turns? Is that the same thing?
Or, I mean, if they're touching each other, it feels like they're just making a single solenoid with the same number of turns. But I assume we're not. I assume they're not touching, I guess. Doubling number of turns and keeping length the same. Are we quadrupling it then?
I guess so. If that's the case, it's 4 times as much.
There's no cancellation happening because the currents are going the same direction?
I don't think so.
Okay. Actually, they shouldn't. Wait, how are they possibly... How would the currents go the same direction? The problem says they are. But if they're connected... Oh, I guess you could make it... Never mind, you can make it do that. Yeah, I don't see what else you would do besides doubling number of turns and keeping length the same. Cook is agreeing. I have a very hard time imagining this. Or like imagining what would happen, but I don't know what else it could be if not this. There's a way you can think of differentiation multiplying a vector with polynomials. You know, functions work here because power series coefficients on the rows by matrix. That will allow d squared dx squared to be d squared, then everything else is smooth sailing. Oh, I have no clue about that syntax error. Same current, you get twice the field, 2 solenoids contributing, also twice the area for the flux to go through. So for the same input current, we get 2 times 2 times the flux, or 2 times 2 equals 4 times the flux. I guess. If I check the answer, do you have any objections?
No, I like this.
All right. 12.
Let's see what Morin has to tell us.
Okay. We're right for part A. Okay, then for part B, it does quadruple. Okay. Without much more thought, that's all you need to know, I guess.
Twice the field going through twice the number of turns.
Yeah. Hey, Terabert. It's going good. We're doing this, on Saturdays I've been doing an Electromagnetic like reading group. So we're working through some problems from the textbook right now. Okay. That was 12. Or 15. Has to do with energy. Consider the RL circuit. Did I pull an image of that? I did not. Discussing 7.9. Show the energy delivered by the battery up to an arbitrary time t equals the energy stored in the magnetic field. Oh yeah, Terabert. There's a pinned message in that chat kind of explaining what happens in like a copy of the textbook. It's pretty difficult to jump in this deep into it though. This is only going to be going for another month or two. Okay, so let's look at what are these equations? Okay, so 7.65. This is just a differential equation question, so I don't think this will be all that bad.
Yeah, we should be good here.
I think I'm specifically looking for at least one diffie-q question.
Yeah, 7.65. So that's coming from Kirchhoff's voltage law.
I thought Kirchhoff's doesn't apply for this because the field isn't conservative anymore. Maybe you probably know more about the circuits than I do, but I thought they were making a point about how it doesn't work in some scenarios.
Oh,
maybe it's only for a changing magnetic field or changing current or something. I might not be right with that. This is an often poorly explained point. Okay. Show the energy delivered by the battery to an arbitrary times t equals the energy stored in the magnetic field plus the energy dissipated in the resistor. Kirchhoff's loop rule does not apply when there's a changing magnetic flux through the circuit. And so that changing magnetic flux is external to the circuit, but it still applies in this scenario where we don't have any external fields. Maybe that's probably where I was mistaken. Cook is saying power from the battery is equal to I as a function of time times V naught. Shifting of Faraday's law is a generalization of Kirchhoff's loop rule. When there is a changing magnetic flux, when there is no changing magnetic flux, Faraday's law and Kirchhoff's loop rule are the same. I was right. That it doesn't apply here. When there's, I guess when there's an inductor involved. Where does this come from? The inductor creates a changing. However, okay.
is it that you have to assume the inductor has zero resistance?
Yeah, like all the resistance is gathered up into the resistor R in that circuit diagram. By moving the loop EMF to the left-hand side of Faraday's law, you can make Faraday's law look like Kirchhoff's loop rule with the inductor dropping a voltage L di dt. Physically, that is not what happens. The inductor is a wire and drops no voltage, but mathematically you can treat it like it does. Huh. And so what you're saying, like, this is basically what we get for Faraday's law in this circuit, and it just happens to look very much like a normal Kirchhoff's law result.
Yeah.
And do you know if it's Kirchhoff or Kirchhoff? I've heard it both ways, but I don't actually know.
I don't know either.
Oh, okay.
In fact, I'm sure I've said it different ways at different times.
I feel like I had a professor who said Kirchhoff or something, but I first learned it with Kirchhoff, and that's how I like learned to pronounce it.
Like Captain Kirkhoff.
You've heard the first one, Kirchhoff. Okay. But you think it's Kirchhoff. Should we just start?
I guess we just integrate this thing, right? So
Um, I squared R is equal to I. I mean, how do we integrate?
yeah, I know. I want to integrate it.
Because I is our function. If we don't cancel this I though, this feels very weird. I guess this it's separable?
Oh, is that what it is? Yeah, we could. Oh, wait a second.
It really hurts me to not cancel the i's, but we could say like 1 is equal to I E0 minus L. Well, it's not really that separable, is it? No, that's not separated. The battery has a constant potential. Oh, I think it is separable, just not in the way that I was separating it.
How about this? Oops.
They're saying to do that for the first step, though. To have an I squared R.
Yeah, they told us to multiply it by I, right? Because I know you were saying, well, let's divide by I, and I'm thinking, yeah, but I want to do that too, but they told us to multiply it.
Yeah, Cook, I don't know what else to do when they're saying the book is saying directly just to do that. But yeah, this is how I think it should be separated. And then you can divide the right side over to the left. Why can't we just
Oh,
take the result of this and multiply by I? This is going to be a weird integral. Like, do we still not get to cancel the I to integrate this? You didn't read the last sentence? Oh, okay. Oh, let me go there. Power conservation will also give a differential equation.
what's constant here? So everything's constant except for I and T, right? Those are our two.
Right.
Yeah, because I depends on time.
So from there, I was thinking we should divide by the right-hand side, but this integral doesn't seem easy unless we cancel the I.
Could we try it?
I guess so. I don't know what else we would possibly do.
All right. Right, we're canceling the I. Let's see what happens.
But like, this is just back to the original differential equation that they solved, and we'll get the same thing.
Yeah, did they do this in the book? They probably did this in the chapter.
Yeah, you get like an exponential.
Yeah.
So that's why I'm nervous that we don't cancel the I, but like what the hell? How is this any different?
Okay, we're trying to show the energy delivered by the battery up to an arbitrary time t equals energy stored in the magnetic field plus energy dissipated in the resistor. Well, energy dissipated in the resistor is I squared R, isn't it?
Yes.
Let's see. So that's energy dissipated in the resistor. Can we add, what do we got? An I epsilon naught. Isn't that energy coming out of the battery? I times
Yeah, so
epsilon naught?
I times V. Yeah.
Yeah. So the energy stored in the magnetic field must be made up of this piece, I, L, di dt. Yeah, that sounds right.
Because that's I times d phi dt. And I think that's Faraday's, or it's like Faraday's law. Because L times I is phi. Or
What was that? What's that? L times I is what?
It's because the way L is defined, if we have like I, L, d I, dt, the book was doing pretty frequently like bringing this L into the differential. And so you could also write it equivalently as I times d phi dt. Just the way the L is defined.
Oh, okay.
And
yeah, see,
I don't know what that is,
I'm
though,
coming
but...
at this from a I'm coming at this from a circuit theory kind of point of view, and I really have to think of it more from a physics point of view with flux and stuff like that.
Yeah.
So what do we have to integrate then? That's where I'm confused. I think I'm gonna scratch what I wrote here. It's not good, right? Let's erase this.
I think it's... Yeah, I assume we have to keep the i's here and integrate that. Like your new last line is probably fine.
Oh, is it?
Oh yeah, too late now. But I think the energy stored by the battery up to an arbitrary time t. That's the IE0 is equal to...
Yeah.
Energy stored in the magnetic field. I assume that's ILDIDT. Plus the energy dissipated in the resistor is I squared R.
Yeah. So we have to integrate something, right? They're telling us to integrate it.
If you integrate it over time, the dt cancels. You can write LDI.
Yeah, yeah, because isn't it like 1/2? It's one of these 1/2 times something squared bit deals, like kinetic energy and energy in a spring, and all those things look like 1/2 constant times something squared. Yeah, 1/2 Li squared. Is that what it is? That I think that's what it is.
Yeah, it is for
Uh,
the. Oh yeah, the energy.
oh, okay. Because this, oh, I got you now. I think I understand it. So we got to integrate everything dt, right? Okay, we got to integrate everything dt because I is a function of time. Okay. Okay, I think, is this, how's this look? So epsilon naught integral I dt equals L integral I di plus R. Is this trouble? I don't like this. Integral I squared. Is this
I don't.
something
Yeah, I don't know
doesn't
what to do
feel
with either
right?
of those dt integrals. And there's like a physics interpretation for what these mean. Um, because like just IDT, isn't that like charge? I squared
Yeah.
DT, I don't know.
Do I need I at 0 or do I just start current 0? I'll put I 0.
They're power integrated over time for different components. So we're in a. Oh, okay. But it's still not necessarily a constant. But like, I guess that's power integrated over time, which should be energy. But what energy? Oh, is that just, should it be voltage?
Can we use Ohm's law there? Because it's a resistor, right? So can we say I squared R is just,
Oh, use IV or like, and V is a constant. Well, it's the energy up to a certain time. One energy is delivered by the battery, another energy is stored in the inductor, another is energy dissipated in the resistor.
yeah.
Energy dissipated in the resistor. Do we know? Is that just the voltage of the resistor? Like, or whatever the voltage drop is? Hey, Anders. And hey to 7 more. Okay, yeah. I think we're maybe not supposed to literally, like, we could integrate
Really?
the middle term, but just interpreting
Yeah.
what the other integrals are is the point. There's literally no more work to do. You just recognize terms. Oh, I mean, Doing the middle interval doesn't hurt though, right? This is a
So I should have this as
energy stored in the battery. Energy in inductor. Move the resistor energy left. Negative sign corresponds to loss of energy in heating up the resistor. Oh. Okay. Well, sometimes they also store energy. Not gonna be smart aleck. Okay, I guess Cook is saying that the more that we should
okay.
Isolate the 1/2 I Li squared term. Oh, or that works too.
Well, I just erased it and wrote the same thing.
Energy delivered by battery, energy dissipated in resistor, so energy stored in inductor. Oh wait, no, I think we're supposed to get the other term over. Like, we want this term isolated, so... I think maybe we do need another line.
Oh, I see. Yeah, gotcha. Okay. Well, it's all the same.
Yeah. Okay, so that is energy delivered by battery. Battery. That's energy dissipated in resistor as heat. And then energy stored in inductor. Okay, that was a little bit confusing for like... We don't actually have to solve an integral, but I guess that makes sense now that we see how it looks.
I see that in physics all the time, these kind of terms where you got 1/2 times some constant times some function being squared.
Yeah, I always wondered about that relationship between like momentum is mv and kinetic energy is 1/2 mv squared. Like I assume there's a reason for that, but I haven't like learned it yet.
Yeah. Force times velocity is something.
Of course, yeah. I don't know. Maybe there's an actual like meaning there, but just it does seem like a coincidence that you just integrate with respect to velocity to get kinetic energy. Oh, is there a stack exchange thread on that? I'll take a look at that after this, I guess. Okay. That was number 15. What does Morin have to say about it?
So it's basically conservation of energy, right? That's what we just kind of looked at.
It seems so, yeah. So they actually did integrate IDT as charge.
Oh, okay.
That's interesting.
Well, that's the one that says quit. Q equals IT.
Yeah. So I mean, I saw that we could do that, but I didn't see maybe the value in it. Differentiating instead of integrating. Could start with the conservation of energy statement. E naught Q equals Li squared over 2 plus integral 0 to Ti squared RTT. Then take the time derivative to get it. Okay. There's not really any value in it. Different way to say it's the same thing. Yeah, the integral version makes it more clear to me. Like this Q could be a lot of things to my brain, but this is a lot more clear to me that E naught times the integral IDT.
Yeah. Yeah, I agree. And I learned when I was doing circuit theory problems that you usually want to look at your variable as either the current, as a function of time, or the charge as a function of time. And you sort of don't want to try and get stuck in between the two different worlds. You either want to write everything in terms of I or write everything in terms of Q.
Oh, okay.
Because otherwise, it's like you're trying to do two things that go two directions at once.
Yeah. Okay. Next one, I have another energy one. Two different expressions for the energy. Two different expressions for the energy stored in a long solenoid are Li squared over 2 and B squared over 2 mu naught times volume. Show these expressions are consistent.
1/2 Li squared. Yeah, we should have looked at this problem first.
Yeah, this one comes after, I guess, but it'll probably be helpful. And so it's kind of lame problem cook, really? I mean,
This
we could just
problem
skip it.
We probably just have to write B as a function of L, don't we? Or L as a function of B?
Yeah, that's the first thing I was like thinking of, like L is B over I? Or and phi is just B times area.
Dr. Cook saying this is a 0-star problem.
Yeah. I don't know. Can we like? I guess we could take that one and just say that B is equal to ugh.
What was that formula you had for B in the earlier problem?
I think it was basically this. Or oh, you mean the actual magnetic field? B is
and oh, that was a solenoid. No, is that what we're doing here? Yeah, we're doing a solenoid. Oh, but that was in terms of number of turns.
I think that's okay to. Or like the small n is like the turns per length.
Okay.
So I guess if we plug that formula in for B and the B squared. uh, mu naught ni squared over 2 mu naught. Volume of what? I assume whatever cylinder encloses the solenoid. 1/2 mu naught n squared I squared V. And we're supposed to somehow find, well, we have the 1/2, we have an I squared. What is the self-inductance of a solenoid? Oh, they don't do it for a solenoid because there's some weird difficulty.
Oh, we worked that out last week, didn't we?
Did we?
Yeah, look,
Oh, we did. Yeah.
we got it here today in number 12.
Right.
Mu naught pi n squared r over L. That's a different n though.
Okay, yeah, and I think we're about to get to that formula, or we're about to make that match if we do what Cook is saying, and know that V is the cross-sectional area times the length.
Yeah, that's kind of what I was thinking of. Bring the length in.
Can we just keep that as an A? And who cares? Pi r squared L. Well, don't I want this L to be in the denominator? What am I missing? Actually, this isn't.
We got lowercase n, so we could change it to uppercase n over.
That's the difference.
Yeah.
N squared over L squared. I squared. Pi r squared L. Okay, then we have inductance. 1/2. Ugh. Yeah. Okay. Li squared. Okay. I don't remember where the b squared over 2 mu naught times volume comes from, but I guess we did what the question asked. Maybe I'll look at the answers to see if they have a point behind that.
Yeah.
Okay, the entire answer is just this paragraph here. Oh, okay. No, they don't really expand on it.
Same thing.
Yeah. Seems like it, yeah. They do it a slightly different way, but basically what we did. Then yeah, they just go right into 18 after that page, so okay. Well, it's a nice change of pace of a problem that's too easy rather than too hard. A rare treat.
It is.
Okay, now it's back into the 2 stars though, so we might.
Well, it was a nice run while it lasted.
Yeah. Okay, what's happening here? Metal crossbar.
This is that thing they called a rail gun.
Oh, is it?
Yeah, I was reading about
Oh,
this somewhere.
okay.
I think that's what this is. I might be jumping ahead too quickly there, but it looks like,
It does kind of have that vibe.
yeah.
Metal crossbar mass M slides without friction on two long parallel conducting rails a distance b apart. A resistor R is connected across the rails at one end, compared with R. Hey, Canton Mew. Compared with R, the resistance of bar and rails is negligible. There's a uniform field B perpendicular to the plane of the figure. At time t equals 0, the crossbar given velocity v naught towards the right. What happens afterward? Oh geez, good luck, Dipion. Does the rod ever stop moving? If so, when? Well, I I think what we're doing is we're increasing the flux through this thing. We might, and we
Yeah.
probably need to worry about Lenz's law as well.
Yeah. Oh, that reminds me. I meant to post something in the reading group
Oh yeah?
when I was looking at physics a couple years ago. I think it was during COVID. I think I was doing one of the online courses, and there was some teachers doing some demonstrations. There was this really, really cool demonstration of Lenz's law. And what he did was he had a metal cylinder, just like a piece of metal pipe, right? I
Mm-hmm.
don't know, a couple, 4 feet long. Uh, just a small radius, maybe a couple inches. And he took a metal ball and dropped it down through the pipe. And it was what you would expect. You know, he puts it in the top end. A second later, it falls out the bottom end. And he does that a couple times. Then he gets another metal ball, puts it in the top end, lets go of it. And he sits there and you sort of count 1, 2, 3, and you're like, what happened to it? And then it comes out the bottom. It's like a magic trick or something. And you know what it was? The explanation behind it
Mm-hmm.
is that well, actually, you might it has to do with Lenz's law. Um, I think it has to do with Lenz's law. Yeah, Dr. Cook knows all about this. It's so cool. It really is like a magic trick. Um,
I assume they're like
but
one of the most magnetic, the second
yeah,
type.
exactly. So if you take a magnetized ball and you drop it down through the regular, copper cylinder or whatever, or maybe it's not copper, I don't know what it's made of, but as it falls, it's got the magnetic field around it, right? That's moving down through the conducting metal rod. And so you're changing like the flux through the surface of the rod as it falls. And Lenz's law acts in a way to try and like set up loop currents in that cylinder to oppose that magnetic field. And so it's kind of like, yeah, the second ball is a magnet, exactly. And so it's kind of like as the thing falls down, it's getting held up by this continual these continual little loop currents in the cylinder, right? And it really is an amazing experiment. It's like when you show it, well, when I saw it, I was like stunned. I was like, what? How is that possible? Yeah. I
That's
got to
awesome.
find it. It was one of those MIT instructors and he was demonstrating it.
Yeah,
Really,
if you're
really
able to
cool.
find it, I'd love to see it.
Yeah, a changing magnetic flux in the metal too, exactly. Yeah, it slows the falling magnet. Yeah, and it's so cool because he drops it and you just sit there and you're counting. You're like, what happened to it? And where'd it go? You think there's some kind of trick inside it, like he's got some magic, tube that's got a spring inside it that can hold something. But no,
Mhm.
it's just a magnet.
That's awesome.
Anyway, but that yeah, it reminded me when you said Lenz's law. I was like, oh, I gotta find that and post it.
Cook may have already found it,
Oh, did he? Yeah, he found it. Cool.
or maybe it seems like it's the same demonstration at least. But
Yeah, it's not the same guy, but yeah,
oh yeah,
let's
we can
check this
actually,
out.
yeah. It is on 2x speed, so it's harder to tell the
0.02
difference.
seconds. Yeah.
But yeah, that's a huge.
Look at it. Get out of here. Are you kidding me? 4 seconds.
Yeah, I think that was a mistake to put it on 2x speed. I want to put it on normal.
Yeah.
That's so long. Wow. I love just his look. Like I feel a little judged.
Look, he's drumming his fingers on the table as it comes down. It's probably a pretty strong magnet he's got there, I guess.
I assume though to make a difference that dramatic.
Yeah.
What's this other one?
A ring launcher.
Maybe we'll do 1.5. Get to the good stuff. Has he launched a ring yet? Maybe I shouldn't just be skipping through this. Oh. Wait, did we miss it? He's literally just launching it only using magnetism. It's the ceiling.
I think he almost put a hole in the roof there.
Yeah. Could have some fun with that thing. I want to go through and hear his explanation after this, but it's a little bit longer than I want to watch like on stream right now. It's a rapid change in current.
Oh, he's got a cut in it. Yep, he's got a cut in it. There's a notch in it, which means you cannot get a closed ring through a closed loop through it, right? Yeah.
I assume that helps. I don't immediately know why. Oh, he added a copper ring that time, and it went shorter. Roof not prepared for the experiment. Yeah. So now he's putting the copper ring on the bottom instead of the top.
What's the difference between the copper one's the bottom one now? Okay.
Not quite as it's almost as high as just the cutoff ring itself. Oop. Okay, so top or bottom doesn't matter apparently. Oh, the cut makes it not launch. I had it reversed. And it's heated up.
Oh, is that what he's got? A temperature gun?
Yeah.
Okay.
Said it's 85 degrees Celsius. I'm surprised he's holding that.
He said 85?
I thought so. I mean,
Yeah, that's a little warm to be hanging on to, isn't it?
yeah, 85. Oh, Fahrenheit? Okay. That's okay then.
Oh, of course.
Actually, yeah, how would it get that? Yeah, that'd be way too hot. All right, that's a cool video.
Yeah, if you know your physics, it makes it a lot easier to be a magician.
Yeah. Well, yeah, Cook. That's why I was surprised that he was just holding on to it. Was 80, if it was 85 Celsius, but no. It was a cool video until I found he was using Fahrenheit.
Yeah.
No. If you're talking to a room full of students, probably better. All right. So what's happening with 26? We're increasing the flux through this loop because we're making the area that it moves through bigger.
Yeah.
And so this is going to get a current. It's going if the uniform field B is coming out towards us, then we're going to get a flux to make a field in the opposite direction. So the current, I think, is going to flow that way
Yeah.
to make the right-hand rule work out there. The magnetic stripes and cards work? Oh, okay. Yeah, I knew that had something to do with magnetism. I think for Fahrenheit, isn't it 212 that water boils at?
Yeah. 212.
Okay. 85 is like a little hotter than room temperature, Canton. It's like hot, like you wouldn't wear a jacket, but not that hot. So does the rod ever stop moving?
No friction.
There's a resistor involved. That is presumably making heat. I don't know if that matters.
Mass M. So eventually kinetic energy 1/2 mv squared has to get burned up in a resistor through the current, doesn't it?
Canton, thank you for the follow. I'm sorry, can you say that again?
So initially we got, so at time 0, we got a bar of mass M moving to the right with velocity v0. So it's got kinetic energy 1/2 mv0 squared.
Right.
And then we start getting electrical power, I guess, getting burned up in the resistor. So doesn't that energy have to be coming from the kinetic energy of the bar?
Hmm. I assumed it would just come from, well, Cook is saying yeah.
Maybe it's one of these ones where the velocity is going to decay exponentially.
I could see that.
Yeah.
F equals ILB opposes the motion of the bar. Because the bar is a current running and it's in a magnetic field.
Oh.
Because the current running this way up that bar is going to attract with the current running that way through the other side. And that's why Bill is involved. They're like, these two sides are going to attract each other. That's why this thing should slow down. Okay.
So we got to find the current, don't we? So if we can get the current as a function of time, we can work out how far it goes, maybe.
Uh,
Yeah, that was in there.
yeah, it wasn't like a big
Document book, that
emphasis,
was
so I'm
in
not
there.
very good with it, but yeah, it's in there somewhere.
It might have been in the, was it this chapter or was it the previous chapter?
Probably the previous one. It might have been in this one, I guess. I don't know. And so do we want to do some type of like MA is equal to ILB to figure out this thing's acceleration? $6.17. Oh yeah, DF equals IDL cross B. Okay. So, oh, well, I think we can use that to figure out E, because we can figure out how the flux is changing. And then we divide up, or we use Ohm's law to figure out the current, because we have a resistor R.
Yeah, sounds good.
So so it's the field B times the area. Well, per time. The area is, it starts, do we not have any other dimensions here, do we? Can we call, oh, we have B for the side length. Then we should probably define maybe an X to start from whatever t equals 0 is.
Okay.
So, oh, well, that's not quite. Maybe we should define X as starting from, so if we want the entire area, X is probably, like, our origin is probably better placed over here.
I got a feeling it doesn't matter where we start it from.
Okay.
You could call, yeah. Yeah, let's just call that the origin.
It's not, this isn't quite right now, but I want to do something like this. This isn't changing. This is just like the flux at any time is the field B times the area of this rectangle, small b times X. But that's not
Yeah,
d
shouldn't
v
that X be
dt.
Shouldn't this X here be a V? This should be the rate of change of X.
Yeah, like a function v of time. Oops.
A function V, yeah. We could just write it as dx dt.
Does that make sense?
And then couldn't you
I think so.
say that's equal to I of t times R? Or something like that.
Um, oh, because this is Ohm's law, yeah.
Yeah, does that look good?
I think. Minus B. Nope. Yeah, no, actually that is good. Maybe I do want. I don't know if it matters, but I guess. I don't know. That seems like something.
If you change that velocity back to dx dt, then we could separate it, couldn't we?
Uh,
Because
oh,
BVR is all constant, I think.
I mean, well, I assume we want I though, because like where I'm going with the problem is that we want to figure out the acceleration of the bar with
Yeah,
Newton's
okay.
F equals ma thing,
Okay.
whatever law
Yeah,
that
so
is.
okay, maybe you were better off with the V. I feel like we're on the right track here though.
Yeah, negative sign. We
You're
do have a negative
you're
sign,
saying
right?
take put
Or do
all
we
that
need
right
another?
there?
Yeah, that's what I want to do. Quick is
Yeah,
saying
looks
that
good.
I might be able to say A is dv dt minus b dx dt r
Exponential
L.
decay of velocity. Yeah, that feels good. I wanted something like that.
dv dt is proportional to minus v. Okay. So then it probably, we do want to go to v then. V
Yeah,
squared.
my bad.
No. We're exploring this together, so it's probably better to say put the variable like right there to be a bit more clear. So we do have to figure out when. Do we have to actually solve this then? I guess so.
Yeah, let's solve it.
Well, if it's exponential decay, it's going to need infinite time. I don't know. I guess let's see how it looks. uh, we'll get.
Oh, right. It's going to take forever to stop, but it's only going to go a finite distance. Is that what we're going to get?
I guess so.
Nice.
And we know our initial condition. V of 0 is V naught.
So that's our C, right?
Yeah.
You know what I want to do now?
What?
I want to look at B squared BL over R
The
times T
units?
and see if it's dimensionless. Yeah, exactly. That's that's what I want to do.
Oh no.
Just to see if we're on the right track.
So that should be
What,
dimensionless,
what do we
right?
got?
That's what we want.
Yeah.
Tesla squared,
Ugh.
length, time. Um, well, the Tesla isn't that complicated, right? What are those units?
QVB. F equals QVB. That's how I've been working out what a Tesla is.
Newton per coulomb meter per second or Newton per amp meter.
Yeah, something like that.
So it's n
I like the
squared.
amp. I like the amp one you had.
Okay.
because we got a resistor on the bottom here.
M M M S.
Isn't the bottom ohms though?
Oh, I'm so used to. I was thinking of R as a radius for some reason.
A radius. Yeah.
Ugh. What's like the hotkey? There we go. And then
Yeah, RC for yeah, Dr. Cook, RC for capacitors and L over R for inductors. That's right.
yeah.
Or is it, or wait, is it, you might be right. It might be R over L. You might be right. It's one of those.
We were just looking at it. R over L. What is an ohm again? R over L is inverse.
Does that mean we got something wrong?
Is my L not actually a length? No, L. Oh, the L is small b in this problem.
Yeah, we don't have inductance here, do we?
Yeah,
The L was
that's supposed to be like
the...
length L, and in this case it's b, small b. Oops. Phobos, thank you. Good day to you. That changes things. Yeah, no inductors here. There's inductance. Okay, so b squared.
We got some electric energy going on.
I did the same thing in your resistor problem. You don't like big L's? Yeah. Big L's are a big L. I was wondering why you were talking about the L over R for the RL circuit. You know, funny enough, I remember the L is a meter though. That actually doesn't change what I wrote down here.
Yeah, I feel like our units aren't working out here.
Are
they?
Well, an ohm is volt per coulomb. No, per amp. V equals IR. Okay. Can I zoom out? It might not be legible, but I can try.
My heat just kicked on. I hope you guys don't hear that.
No, I don't. As a volt per second. Whoa. Does that give us the cancellation? Meters cancel. N squared a volt in second. Can we justify these canceling somehow? Presumably I have a very hard time writing squares with this tablet in Excalibur. Well, volt is newtons per coulomb. Amp is coulomb per second. Oh, wait, no. We're missing a newton. That nearly works, though. Oh, no, and the S's aren't canceling.
A joule.
A joule per
coulomb.
Okay. Yeah, that makes more sense.
Does that sound right?
Coulomb. Yeah, because it's work per charge. So a joule is still just like, that's not going to cancel an n squared, I
Newton
don't think.
times the meter.
I lost a
We
mass.
lost a mass.
I did lose a mass. Oh my god.
Did we? Where'd it go?
Just into the void. It's.
Oh, it went into the void. Okay.
I don't think it's going to fix all our problems.
That was my job. That was my job to keep an eye on that mass. Sorry.
You know what? That makes me feel better. It's not my fault, so I'll go with blaming you, I guess. No.
Doesn't it feel like we had too many Teslas here?
We. Yeah. So one came from the force from a wire. The other one came from the current, depending on the field. We have a capital B squared cook. That might not be right, but we have one.
Maybe we're good. We're trying to cancel everything, aren't we? The coulombs cancel.
Yeah.
Newton squared seconds over seconds squared over kilograms joules. Joule is a Newton times a meter, but we got an extra Newton up there. Kilogram. This doesn't look right.
No, well, a kilogram per second squared.
Joule is a Newton times
That's
a meter.
almost a force. Yeah. Oh wait,
Oh, we got it. Wait, it works. God
yeah, it
damn
does
it,
work.
it works.
Okay.
Kilogram, meter. Yeah, we got it. This all cancels. Damn it. All right.
I mean, so that did catch two mistakes, one with the capital L and one with the small m. So I'm glad we did this. Okay. This is all for part A, by the way.
Yeah, we did catch the mistakes. Good. Okay.
So they want to know when this thing equals 0. And that'll be at the end of time, basically.
Well, yeah.
It will be moving very slowly at some point, but when
So how
t
far does
goes
it
to
go?
infinity.
We integrate it again.
I guess yeah, that's part B. It has. Okay, yeah, we're integrating with respect to time. Okay. Maybe I'll go off to the left to work on that. B is V naught e to the minus b squared over mRT. B squared mRT. Okay, and so we're integrating from 0 to infinity? Well, that doesn't make sense. That's going to diverge, isn't it? If it never stops moving, it can go infinitely far, right?
Maybe, yeah.
No? Oh, I guess no, it won't. No, it won't. I mean, but if the velocity is never 0, I guess it's still converging. Okay, fine. That's just a straight up. Okay, yeah. I. that's not even a physics thing. It's just a math thing. It can go on forever, but still converged. Yeah. Uh, what an annoying amount of constants to deal with. We just want to divide by that exponent.
Yeah.
0 to infinity. We do get a positive number from this, so that's good news.
Good.
Because when we plug in 0, we're going to get positive V naught MR. Oh, go away. B squared.
Yeah,
B
Cook, I
squared.
do that sometimes too. If
Oh,
you got
alpha
like
will be
10 things,
easier.
you just circle it and call it alpha, and you just start using alpha. Yeah.
True, yeah.
Then bring it back later when you've done your work.
And so these dimensions check out because it's the same exact thing that we just did, except we've removed a time and added a velocity, right? This should be distance. Because there should be some seconds that, like, the meter per second there, we should get a second canceling somewhere from the other units. So I think we're okay on that front.
Yeah, I agree. That's distance. Okay, good. So that's part B.
Yeah, and conservation of energy. Well, we know at time equals 0, it has kinetic energy 1/2 mv squared, mv not squared, right?
Yeah.
And at any time that should be equal to something else. 1/2 like mv function squared minus energy dissipated in the, well, that's power, but something involving the resistor. Probably we need like a 1/2. Something squared something thing, I think.
Yeah, the problem is this, right?
Yeah, the last term that I like, whatever there is power, but that's not
Because
energy. Oh, or is that also a problem?
if this is velocity at time t. Well, no, I'm just saying this. If this is the velocity at time t, then this is really an integral, isn't
Yeah,
it? Like
I think that
we've had
fixes it.
to, because the current was changing all that time.
Compute the integral of I squared r from 0 to infinity time and check that you get 1/2 mv naught squared. Oh, okay. So just going straight to the end of the anytime t. Okay, I kind of like, I don't know if that, like, why the second one works, but I do like to take the initial energy 1/2 mv naught squared and show it should match the final energy of that thing from 0 to infinity. So like we can also state this here and check that the right side checks out because we know what I of t is. I is minus BBV over R. Squared R dt, like that. And so most of these are constants. B squared over R. 0 to infinity v dt. And isn't that just distance
V
traveled?
squared.
Well, this is dt, right? Oh wait, ooh, that's not good.
V squared.
Uh, yeah, we
Yeah, V
want
squared, and then
yeah.
let's see what. So
We're not getting v squared out of this. We know what the result of that integral should be because we just did it in part B. Yeah, I mean that's what we did in part B, but it's just that we don't get v squared as far as I can tell. We get v naught m r over b squared. So we don't have the 1/2 and we
nope.
don't have v squared. I'm getting momentum actually.
Oh, come on. I'm losing my
I did lose a v.
draw now.
Oh, that's what you're saying with v squared pen blocks. I'm sorry.
Yeah, I thought it was V squared.
I wasn't following. I thought, okay. I was thinking about v squared too, but as the result that we're expecting, not. Okay. That should work then. I thought you were saying something else. Let's see. V squared is v naught squared e to the 2 minus 2 b squared mrt. Okay, then this should give us what we want.
Oh, I think I have the same Excalibur open like 4 times. Maybe that's why it's not working.
Oh, maybe.
Maybe that's why I showed up more than once. All right, I'm back.
Okay.
Nope, it's crashed again.
No.
It's crashed again.
It might just be getting too big now. But
It's
this is
getting
the last problem anyway. Okay, we do correctly end up with 1/2 and v naught squared once we make that correction. Okay.
Nice, nice.
That's a neat little problem.
Yeah, I think that was it, right? We finished that one.
I think so. So I think I'll check the answer here.
Nice.
Wait, I guess our answer for what about conservation of energy is that it checks out. That's what we were doing. Oh, this was a problem, not or an exercise or whatever. Let me get the answer key for the second section.
I think the problem I saw was the same problem, but there was no resistor. There was no resistor.
So that one, would it never slow down?
Yeah, like they said the velocity would, and theoretically would go to infinity or something. And then
Oh, okay.
I forget what book I was reading it in, but it said they actually have these things and they can accelerate things to like
Oh, and that's why a
hundreds of meters per
railgun.
second in a really short time.
Okay, I guess that makes sense why a railgun would potentially work then.
Yeah,
That doesn't sound
railgun.
right. Cook is saying.
Yeah,
I
I'm
don't know.
probably wrong about something. I forget where I read it. I think
I'm
it was in
usually
another a
wrong.
physics book I got.
Oh, okay. Um, the induced CMF, they don't have a minus sign for their or an R? Oh wait, I'm looking at the wrong section of our work. Yeah, okay, they don't have a minus sign. I don't know why they maybe there's disregarding signs. Okay, they add the minus sign back in later for because of Lenz's law, but I like our way more. um oh, they define capital T as that annoying constant, but I think our expression for
Yeah.
velocity matches. Yeah. Okay.
Yeah, they wrote it as T over capital T. Yeah. Okay.
Total distance traveled is V naught mr over b squared b squared. V naught mr
Is
over
that
b
what we
squared b
got?
squared. Yeah.
Nice.
Kinetic energy throughout is mv squared over 2, mv naught squared over 2. Do it without integration? Okay. Oh, if you take the derivative of each side? Oh, that's what you were saying. Okay, looks like we did the same approach for the integrals in the book as well. And that's the end. Okay.
Very cool.
What's the non-integration way? Cook just sent it.
Oh man, the old school clipboard. Love it.
Yeah.
I got some of them.
K of t is 1/2 mv of t squared. Take the derivative with respect to time. So you get mvt dv dt, which is v of t times ma. And ma is equal to ibb. Okay. Wait, what happens in this from this line here to the next line? You're putting v over with b times b. Is that IR? Oh, that's equal to the EMF. Okay.
IV
B times V
or
is equal
IE.
to the E, and E is equal to IR. Okay. That is a
Yeah,
lot
that's cool.
quicker.
That's cool. That's what I was trying to think of was like, at an intermediate time, like not at time zero or time infinity, but in the middle somewhere.
Yeah, same at first at least. Nice.
Yep. He knows all the tricks.
Yeah. All right, well, I guess that's the reading group for today.
Yeah, and for a
Um,
couple weeks, right?
right. So for 2 weeks, there won't be a group because I won't be in the country. Uh,
Yeah, have a nice trip.
yeah, thank
Have
you.
fun. I've been
I
to Tokyo. I've been to Tokyo Airport, but I haven't been
oh, like a layover?
yeah, Naruto Airport, I think it's called.
Narita. I think that's where I'm flying into.
Narita, is it? Narita? Okay, maybe.
There's a different one that's also close to Tokyo. I don't remember what that one's called. Haneda? Something like that. Um, but for Oh yeah, I'm going to Japan, Cook. Um, just a vacation, yeah. So, but like for the rest of the reading group, there's 3 more meetings that I think we can definitely make happen. But that means either, well, I guess maybe I should ask first. I think I'm going to be around the Saturday after Thanksgiving. Do you think you will be, or do you not know yet?
I probably will be.
Okay. So what we can do then is it doesn't have to be like set in stone, but once I come back, I'm planning to have a reading group again on the 23rd of November. So we can do a third one on chapter 7. And
Okay.
then the next week, which will be Thanksgiving week, we can start on chapter 9 because we're skipping 8. And then
Yeah.
there'll be 3 meetings on chapter 9, and then that'll be the end. If that sounds good with
And
you.
that'll wrap it up, huh? Maxwell's equations, or is that what it is? Maxwell's equations?
Yeah.
Yeah, nice.
All right.
Sounds good.
Awesome. Guess I'll talk to you later then. Unless there's anything
Relativity,
else,
Cook
but
says.
oh, I mean, yeah, I'll honestly the mechanics hasn't been going as well as I hoped, but I'll like I'm very interested
Yeah.
in learning mechanics. I'm sorry, in relativity.
Yeah, that, even that more in blue book, yeah,
It's pretty
it's not
challenging.
easy. I don't know.
Yeah.
Got some tough problems in it.
We can wait a bit more. All right. Um, I guess we can see it
Yeah.
afterward. So
Well,
I think I should have some like downtime, especially on like the flight and stuff, to do some studying as well. So hopefully I
yeah,
can,
it's probably a long flight, right?
yeah, like 12 hours or something.
Do you just go right across the Pacific? Oh, I guess obviously that's what you do.
Yeah.
Yeah.
Um,
Yeah, AOPS, cool.
we start in February if hired. Okay. Is that enough time for you to cover relativity? Like we started in say like December or something? I guess so. That's a good few months.
Hmm.
Oh, some of them they start in January and February. Okay. Well, either way, there's gonna be a 2-week block where it definitely won't happen, so we can always see where you are at once I'm back.
Yeah, I can work around your schedule, guys. I'm not too busy.
Okay. Not sure how it'll work out. Yeah, Cook. It's not like you're obligated to do anything for us. So if it doesn't work out, it doesn't work out. But I'm very interested in at least doing what I can on my end to make it happen, or it's like not being the reason that it can't go through. So
Yeah, good questions today. They went a lot better than I was expecting.
yeah, mostly stuck to
Yeah.
the lower stars.
I know. Thank you for that. Thank you for that.
I think I needed it too. So probably have to do the same for chapter 9, just so we can like get through it.
Yep.
But
All right. Well, thanks, Don.
thank you. Talk to you later.
Talk to you later.
Okay. Let's switch over the stream title and stuff. Actually, let's get the music going first. Well, what playlist am I gonna do? I'll do that playlist. Slightly different from the usual one. Answering math questions from chat and internet. Let me change my YouTube title and category. Oh, awesome, Fembox. I think this is a ton of fun. I really enjoy these problems. Okay, YouTube info is updated. Excalibur is already downloaded, so I can X out of that safely. X out of that. Keep that open so I can look at it. Oh yeah, Cook. I desperately want to play way more Factorial than I have been. I've only played 2 sessions of it. Granted, one of them was a 12-hour session, but yeah, I started. I haven't launched a rocket yet. I learned after my second session that they moved the rocket launching way up in the progression. So I've probably been slow playing it a little bit too much. But I want to play Factorial at least one more time before I leave. I just have too many games to juggle right now that I can reasonably play with how my schedule works. Okay, there are some math questions that were posted to my Discord. I also think I don't know the first thing about solving them. So except once he got to Euler finding, it was just too much time. The oil sucks in Factorio. Anything involving liquids. I mean, I haven't had to set up a serious oil arrangement since the new update. I just have a basic one. That's one where I would shamelessly steal blueprints from someone else, though. In most every other part of the game, I don't steal blueprints, but that one I do because oil is just too complicated to be fun. It's called Factory and it's about building a little factory. You beat the full game years ago? Yeah, same. When I first started my stream, I was doing a modded playthrough of Capacitor because I had already beaten the game multiple times and had a mega base. But then once the Capacitor playthrough ended, I didn't have much else to do, I feel like, in that game. So then I started playing Satisfactory, but then I rage quit that because it's a stupid game. And then I've been playing kind of random games on a rotation. GM Luca, yeah, please do. In the meantime, let me look at this thread that Cook sent earlier about energy and, or sorry, kinetic energy and momentum. I think is when this thread came up. You forgot YouTube exists, Joseph? I thought that's how, yeah. I remember that. That's how, like, you initially came to this stream, at least. I remember seeing your name and like your crazy name there in YouTube before seeing you in Twitch. Oh. Yeah, I agree, Joseph. The people on YouTube seem to want to stay on YouTube for the most part, but like, I definitely think that the math community on Twitch is a lot, as far as I've seen, it's a lot more interesting. Maybe it's just a niche on YouTube that I'm missing. Gianluca, I saw you typed in the Discord. If you were to post your problem there, ideally in the math discussion or in the math homework help threads, and put something in chat to let me know, because I don't always see like Discord messages as soon as they're posted. Around my mom, the guy who posted that answer is an interesting character here, looking forever to go down. He's a genius, but I think he also went crazy. Indeed, to have solved cold fusion. So you're getting banned from physics discussion boards all over the internet. He was a Harvard undergrad in the 80s or 90s. Everyone's about him when I was there. Wow. Yeah, the Once is Lot thing is cool. I want to go back and watch this video from the start, off stream. Gianluca. Ugh. Calls himself the next Newton. Those are big words. Incredibly bright, but not the next Newton. Yeah. This is a really interesting explanation. It's getting really complicated, but one of his most popular answers. Okay. Kinetic energy is a result of integrating the force with distance. Integrating force over distance? I don't know, Tertar. I'll drop the link to this thread in here if you want to have your own copy to read. But this kind of stemmed from like me asking about like why does, like, you know, if momentum is m times v and kinetic energy is 1/2 mv squared, is there a relationship there? So integrating x dx is 1/2 x squared. I guess. I'm not sure how that works with when like the v is involved, I guess. Oh, it's x prime. Oh, like that. I get it. It's x prime, not just x. Huh. Oh, Force. Well, it's X double prime though. I don't know. I'm gonna keep on reading this for now. Tells you why it must be true. Okay. Which implies that E is quadratic. Wow. Hmm. Oh my god. Okay. Sorry. This answer is a long one, but it is like it's actually friends with my mom. Right, my mom. I kept on saying my mom at Cornell. Hmm. My mom. Okay. It's hard to do like double M and then N for me for whatever reason. Okay, this is too complicated for me to want to read right now. As soon as the lever is getting involved, I'm tapping out. Hmm. All right, interesting. Um. Okay, I see Gianluca posted their question. The text with the image, the other is the translation. Okay, we probably want both of these. Okay, let me get that going. Oh, this. Oh gosh. Okay, this looks like E&M. Let me get the file you posted. It's like, yeah, these are capacitors. Oh my god, please stop doing things, computer. Yeah, we did look at a capacitor kind of like this. Yeah, thanks for writing the translation to Gianluca. So we have. Oh, there's a dielectric though. Oh, we haven't done those. Can we figure it out anyway? It just multiplies the capacitance? Okay. Capacitance is area epsilon naught, or epsilon d, epsilon of the dielectric, kappa. Okay. We want the equivalent capacitance. Knowing B is connected to a potential, oh gosh. A dry, I assume that's a mistranslation, a dry bone, but, or maybe that's actually the dielectric, I don't know. It doesn't matter, that's just the material, I guess. We want the equivalent capacitance and the charge on the capacitor system. Oh god. How did this work again? Uh, can I scroll up in our reading group and see how we did the simpler version of this problem? Would have been in chapter 3 or 4. Oh yeah, and Felix posted that different way of thinking about it. Um, I found the thread, or like the spot in the Discord where we were talking about it. Um, let me just open that up in an actual thing. It was chapter 3, 3.21. Why does that scroll so much? Okay, what was the answer to this? 3 epsilon naught A over S? Oh my god. Should I look at the answer from the book? That might be more informative. Because honestly, I forget how this even works. Oh, we did take different Gaussian surfaces and figure out a relationship. That's kind of all I remember, though. $3.21. So how do we go from the field to the capacitance? Q equals CV. Yeah, that sounds right. Just when I thought I was out of the reading group, they pull me back in. Um, I think I'm going to get more mileage by Googling this problem. I'm going to be honest. This is going to take me a long time to figure out with my own brain power here. Oh, yeah, I saw that. Jackson had also asked me a really weird statics questions with a bunch of hinges and stuff on Thursday, and I didn't know how to start it. I didn't read the actual problem that they had given to Zach, but I assume I would have been similarly lost. Okay, let's see how far that gets us. Something very good just happened. I have to read a book for Dutch because you live in the Netherlands, and the book's actually very informing. I kind of changed my mentality while being at page 25 out of 150. Oh, nice, Lucas. I'm not gonna try to pronounce that, but saying the word dingen makes me giggle. um, the misery of things. It sounds sad. uh, yeah, we would spell it misery like that. But that's the right idea, though. It sounds like. No, I mean it. English words have weird spellings. Misfortune. Okay. Well, crap. I can't find the answer. What is this? That scares me. I'm going away. Gianluca, I don't think I can do this one. I think it's too hard for me. I'm sorry. So if you leave it posted in the Discord there, someone might be able to answer it. But yeah, I don't think I know how to do this. Hey, Babia. I'm doing good. How about you? Give me looking life at the town, which is very poor. Everyone drinks something. Rich girl comes to town. Everyone feels bad. Oh, okay. We're just looking at electricity magnetism question from Gianluca in the YouTube chat, but this one it's a little bit beyond me, so I'm about to move on to something else that I'm not sure of yet. Sounds good, Gianluca. I'm sorry. I'm gonna keep thinking about it, and if I can figure out, I'll get back to you because I feel like I should be able to do this, but just right now I feel like my brain can't handle it right now. What's your question, Babia? I have a bachelor's in applied math and a minor in computer science, Lucas. So I don't have a degree in physics. I'm just studying the physics because I've been enjoying it. But yeah, Fembox, I think I need to. The reason I don't work it now is I think I need to relearn how this 3.21 problem works and then learn how dielectrics work, and then I can start solving this problem. And that's more brain power than I have right now, and more time than I want to spend on stream on one thing. Exactly, Fanbox. I feel the same way. I only remember the big idea from each of the previous chapters. The nitty gritty, who knows? Yeah, Bavia, if you could, that would be amazing. It's that's a link to my Discord there, and it's posted in the math discussion channel. 6 way better second time around, yeah. So the image is the original text, and then they provide a translation there. With some other channels. All right, Lucas, thanks for saying hi. Oh yeah. I don't know if any of them are live right this instant, but those are the people who do math help who I can recommend. Yeah. Doctors change the permittivity of the medium, right? They do, yeah, Tiratar. So Dr. Cook was saying before that like you have an epsilon D rather than epsilon 0. I mean, it's hard because in studying math. Oh, yeah. I felt the exact same way when I was studying math. My physics class was, I found it one of the most difficult ones that I took in my degree. But being able to study it in a self-directed way after graduating is kind of awesome. Chaotic Dude. I saw that, yeah. I went and followed him right when he said that. All right, I have technically read chapter 4, and I am finally moving on to chapter 4 of this book because I spent way too long on that one problem in chapter 3. I have read chapter 4. I took a few and I will check them out. Awesome. Yeah, the one caveat I'll give is like Tells Teaches in that list will primarily play games and then only switch to math if someone asks a question. And Danny Highway is on a hiatus right now. But other than that, you'll be able to find like dedicated math streams from all those streamers at some point. Just finished this a few days back. Oh, nice. Okay, Journal++, I have it at the ready. Let's start pulling problems in. There's only 3 options? I guess it makes sense. There should only be 3 options. Another great chapter to work on? Okay. Do you pull on opposite ends of a rope, each with the force F, the tension in the rope? I gotta imagine that it's 2F. If it's not 2F, I feel like something is wrong in the world. Because I feel like I could imagine if you had like a pulley that was holding it up and both people were like pulling away from it, that should be 2F also. I feel it's too simple though. I feel like I'm being tricked when I answer C here, but it just seems like the right answer. I don't know. So You're right to think that is too simple. It's more complicated. Oh no. A pulley also applies a force on the opposite end. I can't justify it being anything else though. Can sell the first one. Oh, I mean, if you can just put it as a reply to them in Discord, I think that would be perfect. Fabia, thank you so much. Yeah, I mean, even an answer to one of them is better than none. That's really appreciated. Thank you. I should say I really appreciate that. I'm gonna check. I feel like I'm being conned. I'm gonna check the answer. Fuck. What? Dude, I don't get tension. Common error is to double F because there are two people pulling and to say the tension is 2F. That is incorrect. It's every piece of the rope pulls on the piece to its right with a force F and also on the piece to its left with a force F. These questions bring back memories. I'm here for the knowledge and power, and it looks like I'm all out of power. Hey, Tyler. The wall still pulls on the rope with a force F, so the setup actually hasn't changed at all. What? I'm gonna ask. Their explanation for tension made no sense to me. Like this entire like section here. I probably shouldn't lean into the mic like that. I feel like I do that a lot. The way to think of tension is in a robot is too much and cutting it at a given point. Each piece of rope this cut produces will be pulling on the other one. I don't know. But if you think of a cable hanging off the ceiling, the tension is equal to the weight of the mass, despite the ceiling also exerting a force. Or think of a stretched spring, the right half pulls on the left half, while the left half pulls back on the right. I guess that spring thing makes sense. Okay, put that away for now. I need a drawing. Okay, so that's not what I want. That person is pulling with force F. That person is pulling with force F. If I want to know what the tension at, say, this point in the rope is, we know it's not accelerating. Or like, we know the rope is stationary, so it's being held together. So at this point, you have one force opposing that force and another force opposing that force, and you isolate one of them and call that the tension. Is that what's happening? That's it? Think about what happened if one force was greater than the other. So small f there, big F there. At this point, we'd have a small opposition. No? I guess maybe I have the direction reversed where, well, no. The rope should accelerate to the right. What is... I'm not drawing this right. Like, it should be that this little bit of rope in order to not break. Shouldn't be pulling to the right? I don't understand how the tension works if one is more than the other. The tension is just the smaller force. Oh. Because we want the net force to be F1 minus F2. Or F2 minus F1. So that only partly cancels with that. I guess so. Okay, yeah. I think I can imagine in like the tug of war that's happening, the rope only needs to resist breaking from that smaller opposite force, so the tension is only that little bit. All the rest, all like the spare bit of this force is going towards accelerating the rope. The person exerting the greater force will have net force himself minus the tension. Tension is the force exerted by the weaker person. Okay, yeah. I think I see that. Is it weird if I feel like E&M is easier than this? And I feel like mechanics should be easier of the two. Find E&M much harder. I'm not saying it's easy, but this has been way more of a challenge to me than I thought it would be. Skeleton. Yeah. All right, 4.2. You accelerate 2 blocks in figure 4.2 by pushing on the bottom block with a force F. The top block moves along the bottom block. What force directly causes the top block to accelerate? Well, my first instinct is to say friction. Because of something. I should not draw that arrow should come out to the right for F. Like I know intuitively that like if you have like a block of wood on the bottom and a block of ice or whatever on the top, the ice, I mean, it probably, well, okay, it has to be some pretty dang slippery ice, but like I can imagine if something purposely has no friction on top, that it's not going to accelerate with it, it's going to slide right off. I have a hard time like making that work in the free body diagram, to be honest, though. I mean, are they just? Could you consider them just as one rigid mass? Hmm. In which case, the answer would be D. Or like, if you took the same setup and you pushed really quick, uh, the top block wouldn't go with it. It will just fall straight down. Like the same way that you can like yank a tablecloth from underneath a bunch of plates and stuff. They both apply friction to each other. Yeah, I'm just confused how to actually like draw it, because shouldn't the friction, like the friction, like if the motion is to the right, then wouldn't friction be acting that way? But that feels weird. Like, I feel like what I'm looking for is whatever thing is acting to the right on the top block, but like, friction is an internal force, so the sum of all internal forces should be 0 in order for the net force to be F. So internal, if you consider the two block system. Like, are we saying then there is a force like that due to friction, but this existing implies there must be an equal and opposite force opposing the friction, and that's what's doing the magic here? F? So the friction is still indirect then, and I feel like the answer is D. Because the actual, like, I feel like the answer to the question is whatever this arrow is pointing to the right, and I feel like it's still F. Fabia, oh, you did it? Oh, thank you for that. Let me ping the person who posted the question. Actually, let me look at it too. Just out of like curiosity. Last procedure were equal and opposite, the small block wouldn't accelerate to the right. Oh, I guess you're right. Yeah. Okay. Opposite but not equal. Nothing backwards is possible. I may be confused on the wording where they're saying directly. Like, this only happens because the friction exists. But it also wouldn't happen if I wasn't applying the force to the block. So which one was more direct than the other? They're credit versus that indirectly cause the top block to accelerate. There are quite a few forces that indirectly cause the top block to accelerate. Yeah, because I'm kind of realizing that, like, for the bottom block, that force due to gravity is actually like both of the masses together. Imagine you are the top block. What is accelerating you? I guess imagine that I can't see whatever force is being applied to the bottom block. And I guess it would be the friction. Like, if I were to jump right before that force started, I wouldn't be accelerating. But, like, I'm gonna be honest, when I went to check the answer for number one, I saw that the answer for number two is B. Well, I mean, it's really like I know how this works. I just don't know, like, I feel like directly is open to interpretation. I don't know. No, that's fine, Cook. I hadn't, I guess, made it my final answer, but well, no, I don't know. Confirmed with Regis, yeah. Is that your final answer? Okay, I guess your explanation there, Fembox, with like imagining myself as the top block and asking what's actually accelerating me answers the question, but like I don't know. I don't like the wording of this. Is that a song? What do you mean? We're talking about Who Wants to Be a Millionaire, the game show. No, no, no. That's what would happen in the game show. That they would play a song like da na na na, and then the lights would like literally like move downward. Static friction would be more accurate. I remember like watching that, making little person references. I know. I was talking before about like it's kind of like when you yank a tablecloth out from underneath like a bunch of plates and cups and they don't move. I guess it's like the opposite scenario where rather than having very little friction, you have a very big force that overcomes the static friction. But like they're all essential pieces of the puzzle here. That's what I don't like about the question. Like you need the applied force, you need the normal force, and you do need the friction. So calling one more important than the other just is weird to me. Friction doesn't have time to act. Oh. Whippersnappers, all of you. It's a negligible change in velocity. I still don't like that question, but let's just keep going. Three boxes are pushed with a force F across a frictionless table. In figure 4.3, let N1 be the normal force between the left two boxes, and 2 be the normal force between the right two boxes. I bet this is a. No, not necessarily. Not necessarily. No, 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 no. So the I think no. Well, wait. So in order for the box not to deform, I was thinking, or is it? Like it's got to have an opposite normal force, N1, right? But not necessarily. I mean, they're not, this is my struggle. I wasn't getting this like. A lot of the explanations that they gave in chapter 4 don't make sense to me because if N1 was pointing to the left and it equaled F, the first block wouldn't move, but they are moving. Another question from a paper I gave? Oh, really? Hey, Pen. The good box deformation question. Um, There's a mold infestation in the greenhouse. Oh, that sounds terrible to clean up. The thing is accelerating to the right. So I think it's probably not A. You saved the marijuana plant, hopefully. Fingers crossed. Joel, half an hour to an hour. It's probably how much longer I'm going. Sorry if you put that a while ago and I didn't see it. No one wants a moldy bud. Nope. Apply the same logic to the 3M box and you have the answer. Moldy bud's dank weed, if I recall correctly. Oh, so it's the second box. Experiencing a total rightward force of F minus N1? Is that what's happening? No, for the E&M, so I've been doing like some mechanics just like in the downtime of the stream, but the E&M, we're currently on chapter 7. We just had our second meeting on chapter 7. Yeah, this is Morin, what I'm doing the box problem from. The E&M, we have like 4 meetings left. One more on chapter 7, and then we're gonna do 3 on chapter 9. But yeah, this is like I've been wanting to like relearn mechanics a bit, and I'm getting my ass kicked by this book, and that's just kind of how it is. I see Cook is saying new, but wait, this is by knowing each box has the same acceleration. Yeah, I was just realizing that should be N1, I think. Because of how N1 is defined. By knowing each box has the same acceleration, you can infer the 3M box must have a force of 3M over M plus 2M plus 3M. The other arrow is also wrong. F doesn't act on the 2M box. That's why it's F minus N1. Ugh, okay, wait. Sounds good, Pen. I hope Mary Jane pulls through. There needs to be some force out on the right. But like... Oh, I saw something about November 5th. Yeah, these N1s shouldn't agree with each other. That doesn't make sense. You're right, Territar. Just want to wait to Canada and sleep in your basement. Okay. M is pushing to the right on 2M. And so 3M is pushing to the left with N2. 3M is getting pushed to the right by N2. Well, Fenbox asked about the basement pen, okay? It's a basement suite? Oh, okay. Well, I mean, I was hoping for like a creepy like crawl space. That's what I was imagining. Fenbox just like sneaks in. I mean, doesn't there have to be some type of force to the left on the 3M box, though? No? Well, I know that F needs to be greater than N1 in order to have a net force to the right. And that's why I was saying that. That's why I initially put F minus N1 there, and then I got yelled at, so I took that back. But I guess that means that N1 should be greater than N2. And so theoretically should be distinguishing between these two somehow. Well, no, it can't be B, because that means N2 is greater than both of them. Never mind. I feel like... I mean, shouldn't there be some type of relationship that looks like answer B, though? I don't know. Maybe if it's not if it's frictionless, maybe. between boxes 2 and 3? Where is it easier to smush them? Oops. Yeah, they have a net acceleration to the right. Ice physics. Uh, we're just getting to the bottom of number 3 right now, and we're 4 will be in a minute here. Hey, Clunk. Joel. Yeah, I think so, Pen. Why am I doing that? I don't see how partial derivatives come into play here, Joel. Do I have an Instagram? No. Yeah, Felix, I think with the spider, I don't really get. I'm going to be honest. I feel like the bigger one should be harder to push, but I think it's the opposite. But I don't know why. So, Joel, I'm not sure why we need partial derivatives here, because arc length S is equal to R times theta if theta is in radians, but theta is just a constant in this question. So I don't think we need partial derivatives. If the theta was also changing, then yeah, sure. But don't we just take the derivative with respect to time of each side here? Oh wait, area. Sorry, this is a harder question than I thought. What's the area of a sector? Theta r squared over 2? Okay. You know what? I'm much happier in a world with no spiders anyway, Fembox. I mean, there might be a reason for partial derivatives here, Joel, but I'm still trying to figure it out. Theta r squared over 2. No, I still think we don't need partial derivatives here. That theta is not in radians? Babia? I think this is fine what I've done here. And I think there's an arc length hidden inside this where we can say, there's a theta times an r in there, so we could say it's also s times r over 2. Something we could be that about things that have more than 6 legs. You love spiders, you never squish one unless it was attacking me. If a spider is outside, then for the most part it's chilling. If it's inside, then that thing's dying. Six is the acceptable upper bound. It's the supremum. 5 legs would be more freaky than 8. Yeah. Okay, I assume what we want to do here is take the derivative with respect to time of each side here. And these are both functions of time, s and r. So this is kind of like implicit differentiation. It's going to be a product rule because s times r. So it's going to be r over 2 ds dt plus s over 2 dr dt. I think that's what's happening here. Yeah. I hope. And we know from the formula for arc length that ds dt equals dr dt times theta. You want to see Fibonacci 1, 2, 3, 5, 8? Stuff that makes me uncomfy. And so we want to know what dA dt is. The radius we're given is 20. ds dt, we're saying it's increasing at a constant rate of 0.003 centimeters per second, plus we don't know exactly what theta is. Hopefully it cancels though. If s is equal to r theta, then this s is equal to r 20 times theta over 2, and then dr dt, oh no, yes, dr dt is equal to 1 over theta ds dt. Okay. Oh, sorry. We know what ds dt is. 0.003. And we're increasing. Okay, so the thetas cancel. That's good. So 20 over 2 is 10. 10 times 0.03 is 0.03. Take a 0 off. Centimeters squared per second. Plus, same thing on the right side, 0.03 centimeters squared per second. So just add those two together, you get 0.06 centimeters squared per second. And so it's increasing at that rate. So I think this is our answer here, Joel. and the units check out because centimeters squared is area, and it's the rate of change of area. So centimeters squared per second, area per time. Don't make sense when they try to use average to explain everything all the time. Yeah. Does that make sense, Joel? It's kind of a weird problem. I haven't seen one quite like this before, but just kind of start doing some calculus and hoping that it works out. That's what I did, at least. Take the mode. Oh yeah, mode would be better than median, even though they'll come out to be the same, hopefully. All right, not seeing anything from you, Joel. I'm gonna scroll back up. But let me know if you had a question on that. All right. Now I'm looking at number 4. Half of all Canadians make under the median household income. Wild. That's true. Can't deny it. Two blocks with masses 2 kilograms and 1 kilograms lie in a frictionless table. A force of 3 newtons is applied as shown in figure 4.4. What is the normal force between the blocks? Ugh. Okay, so do we know that total mass 3 kilograms times whatever our total acceleration is a. That doesn't make sense. That's not what I wanted to do. What do I want to do? If it's frictionless, I feel like they should just. I feel like there shouldn't be normal. Or I feel like it's 0, but that's probably not. That's probably wrong. Ugh. Do they say about normal force? It's being pushed to the right with 3 newtons. I assume it's being pushed to the left, but by some normal force. This is being pushed to the right by that same normal force, right? Ugh. Oh, is the normal force? I get it. Does it only depend on the 1 kilogram? Yeah, I guess it's just one. Because that, yeah, okay. Oh yeah, like the literally the title of the chapter is F equals ma. It's like just the equation. It's kind of a funny name for a chapter, but like chapter 4, F equals ma. Not Newton's laws, but F equals ma. I thought that I thought this was the answer. Um, well, the normal force it should be. I guess the total is it the total force minus 2 times the acceleration. Why do I think that? Besides, it gets the right answer. I think. It's like you skipped a step, but it checks out. I mean, yeah, I don't have an actual justification for this. The block is accelerating at 1 meter per second. Uh, and so I was thinking that the net force driving it is 2 times 1. No? Yeah, no. Yes? Not like mass times acceleration is equal to the 3 Newton force plus the normal force. This is great notation, by the way. Capital N is both a unit and a value. That gets a negative, but I guess that's okay because it goes the other way. That's not 2 times 2, by the way. That's 2 times 1. What am I doing? Okay, that's M times A. Those are the total forces. I need a subtraction, don't I? That would make the signs agree. Okay. Okay, that's a justification. I think. Ugh. This is a creepy little hand, by the way. I don't like it. It's my strong hand. Ugh. Is that how we talked? I can't remember that. I don't remember which scary movie that was. It's a few days too late for Halloween. Yeah. What? Oh, yeah. 2 or 3? Okay. In the system shown in figure 4.5, the ground is frictionless. Oh my god, we have ropes and multiple blocks. This is my worst nightmare. I'd so much rather get the self-inductance of 2 solenoids inside of each other than do this. This is terrible. Ugh, okay. Got him. Book him. Making references that Zoomers won't get. Love it. The figure in the system shown in figure 4.5, the ground is frictionless. The blocks have mass m and 2m. And the string connecting them is massless. If you accelerate the system to the right, as shown, the tension is the same everywhere throughout the string connecting the masses because the string is massless, the ground is frictionless, the ratio of the mass is 2 to 1, the acceleration system is non-zero, the tension is the same throughout any string, no conditions are necessary. Mashed potatoes are never the same after that movie. Fabio. Yeah. Ugh. I feel like it should just be E. They. Oh, I wasn't even showing my journal plus plus. Good thing it was basically the same view as the textbook. They were saying something about strings and the tension and the something. Where where were they saying that? They were saying that. I'm not crazy. There we go. Conservation of string. Oh, never mind. That's not. Okay, I was misremembering what it was. I was wondering about the springs as well, but I didn't see it in the spring set section. I thought they were saying something more about strings, but maybe not. The tension is the same. We're looking at number 5, 4.5 Timopron at the top. It's frictionless. I'm not saying that's what the answer is. I'm just reminding myself that this is frictionless. The chunk must have 0 mass, but also accelerates to the right with the boxes. Scrimp is also saying it's because it's massless. That F equals 0. It has no tension. Or just that the tension cancels on each side, rather. Dude, tension is the worst. Who even likes tension? Okay, I guess I see it. Fraction too much friction. It's the same as the box's problem from before. Or like it essentially turns into the box's problem from before because the string is massless. Timo, I think the point they're making is that M is 0, so it has acceleration, but whatever's happening, like, I think just strange things happen when you assume something physical has no mass. It is accelerating, but M equals 0 and F equals MA, so. Because the string is massless by the statement of the problem. Bonus question? Oh, good, because I've been doing so well on these. Imagine now the string does have mass. Yeah, the boxes do have mass, Timo. How must the tension in the string vary along the string? Is it because if it does have mass, and you make a cut at some point, this chunk has much more mass than the other chunk, Um, and if the acceleration is the same, but this side has more mass, then surely it has more tension on the left side. It's more, the tension is higher on the right side. Dude, fuck tension. The tension on the right has to drag the 1M block. They're both dragging the 1M block, but the shorter bit here has to drag the 1M block and the bigger side. Then they give me started on compression. Okay. I'm just gonna accept it. Pen Center, I've been finding E&M way easier than mechanics, and I feel like that's backwards from how most people feel, but I I've been loving E&M and hating these problems, but I want to learn how to do them. I'm not enjoying the mechanics though. I'm gonna plow through it, but I'm not a fan of these. I wonder if I would prefer the harder Morn book, to be honest. If you hang something with the intention is equal to the gravity on that object. Imagine we hang a chandelier with a massive chain. Is the tension equal throughout the chain? If not, where is it greater? Well, I guess... I wanna know... Do the kids know that song? As long as they're making dated references. How do you draw a chandelier? I think I'm kind of drawing a menorah, but that's a chandelier. Okay, by the same logic, this upper part of the chain has to hold up the lower part of the chain and the chandelier, whereas the lower part of the chain only has to hold up the chandelier. So the tension is greater in the upper part. So it's going to break at the top. I just turned the picture sideways. I guess so, yeah. So like in the original question, is the 2M block just irrelevant? You cook the shit out of it. This reminds me, it's not really that related, but it reminds me, I think it was in my differential equations class. The most dreaded problem I think we did in that class was, I don't remember, or maybe it was like my applied math class. No, the problem I'm about to say isn't really relevant. You had to, you have a chain laying on a table. Where did I do this? Maybe it was in physics class. I don't know. And just a little end of it was hanging off. And I think you had to get the amount of chain hanging off the table, like I think we called it X or something, at any time T, and that was something crazy. It's almost time for me to cook the shit out of some dinner. Same here. I don't remember exactly how you did that problem. I think it involved a differential equation though, because the mass that's being affected by gravity is changing. It's in Morin's red book. Okay. Only a 2 dot? Oh my god. That problem seems very satisfying to solve, Territar. It is an interesting problem. I wouldn't mind taking another look at it at some point. You had to quit that book? I don't blame you, Pen. It'd be a very, like, it's literally your first time you've ever, like, actually studied physics. That's a tough ask for someone it's your first time. You're probably way better off using a book that's not insane. It's the honors freshman mechanics book at Harvard. We showed over for hours and hours, but it put hair on our chests. Have a 5 on the AP, physics C, mechanics to get into the class. Wow. Meanwhile, at my college, I took the AP Calculus BC class, and I had credit to not have to take Calc 2 in college. But my advisors were like, oh no, you should take Calc 2 anyway, because college is hard, it's going to be hard. It was a complete waste of time for me to take Calc 2 there. I didn't learn like anything, and it was stupid. Ugh. Dude, my math department could not get a good advisor to save their life. It was so annoying. I ended up just reading the graduation requirements and stuff myself and going to like department chairs and asking them to do it for me. Because the advisors were such shit. And even like the math department chair was like, oh yeah, I gotta go yell at that guy again for giving bad advice. Went to residential STEM high school, so able to get ahead in math and physics, really changed my life in hindsight. Oh, nice. You mentioned it's like a differential equation form x double prime equals x. Maybe a territory. I don't remember. You do a great impression of me. Does your college like have good advisors, Pen? Do you have the same issue? You have to yell at the advisor all the time? Oh no. That sucks. Get rooked. Can I ask an exercise from elementary group theory? You can certainly ask. There's a good chance I won't be able to answer it, but I bet there's someone in chat who can. You might be interested in actually checking out Penn Center Stream in particular, because he's been studying group theory. But you're welcome to put your question here too, and we'll try it, or at least I'll try it, and someone might jump in and save me. If it's easier, you can put it in my Discord too, if you prefer to just do a screenshot, but you can also put it there in chat, whatever's easier for you. In the meantime, I'll keep on doing these study questions. By the way, welcome and get rooked. You're in a plane accelerating down a runway during takeoff, and you are holding a pendulum. Of course I am. That's what I always do when I'm riding a plane. Say a shoe hanging from a shoelace. Oh, okay. This feels like a relativity thing. I think I know what one wants for 4.6, so this first question said we're not a fan of the wording. So, okay, if I'm just on the Earth, and I have a big enough pendulum, it will start moving around, right? Like there's like a massive pendulum somewhere on the Earth that moves around because of the Earth's rotation. Like, Morn always takes his shoes off when he flies. Imagine that the person next to you in the plane takes his shoes off and holds them up by the shoelaces and observe how his shoes move. It's just wafting the scent, you know, that foot stank through the plane air. Get rooked, put their question in chat. Okay, hangs up by a string, gets out of pocket protractor. Yeah. Okay, so let G be a finite group with the order of G equals n, and n and m are co-prime integers. Then show for all A and G there exists a B in G such that A equals B to the m. BM? Okay, so sorry, I just have to get the poop joke out of my system. Bum. G is order n. For all A and G, G is finite. My algebra is really rusty. It's been a minute since I've opened up that textbook that Penn's been using. This makes sense by division algorithm. That seems like it could be helpful. What do we want to divide? A to the n equals 1. Just take k so that... Is it true that A to the... Wait, oh man, is my algebra that rusty? Take k so that km mod n equals 1. B equals A to the K. What is this saying? And M and N being co-prime assures you that this always exists. I thought B had to always be the same. Oh, that would be weird, yeah. Get booked. Does that make sense to you? I'm still working out, but the important thing is whether it makes sense to you at least. It sounds like we know that A to the N equals E. Yeah, I don't know. I would need to try with actual numbers, I think, but this might. I need to just relook at an algebra book to really understand this, but it makes sense. Okay, cool. Thank you, Point Gallus, for finding the answer then. So yeah, get Rooked. If you're interested in more math streams in general, I'm not too good at algebra myself. Penta is probably the best place to go for these days for kind of like algebra discussion. But I bet Ian Stu could be able to help with this type of stuff as well. And in general, there's a whole list of math streamers there if you're interested in just kind of like math content on Twitch in general. And feel free to come by and ask it in my stream too. I just would probably hope that someone in chat bails me out of it. Oh, nice. That's a different way of doing it, Cook. That's maybe more along the lines of what Fembox initially said with the division algorithm. Oh, okay. Yeah, I think I see that. I guess, yeah, I guess maybe what Point Gal said doesn't necessarily say how to find that K. And I think maybe Cooks does, but either way, it should be. That also seems like it should work. Okay. Back to let's suffer through a few more problems, then I think I'll wrap things up. You're okay. A plane is accelerating down a runway during takeoff. The whole plane thing just feels like a red herring, because you could always say, you know, consider the Earth rotating, but then also consider the Earth orbiting around the sun, but then consider the sun orbiting around the galaxy, and then consider the galaxy doing whatever the hell our galaxy is doing, and like, you know, keep going bigger and bigger. I'm trying to figure out like what the plane is doing here. if anything. But if I'm on the plane, like, I don't know. I'm confusing myself because I'm... Do I know the plane is accelerating if I'm on the plane? Wouldn't I have to be on the ground? I don't know. That's why I'm thinking about, like, relativity. The plane accelerating, is the shoe also not accelerating? Yeah, I mean, I guess it's getting carried along. I think I'm involving relativity and I shouldn't be, but, like, I don't know. I don't know. I'm just confused, like always. The point holding the pendulum is acceleration. Okay, that's probably a good point to make. My body plus the shoe continue moving forward. But if you treat the plane as the inertial point of reference, then the pendulum was accelerating. Oh. The only thing acting on the shoe is the string. How must the string be arranged so as to affect the necessary... Oh, what am I doing? Acceleration. Phobos, between 3 cities? Dang, busy day for you. But hey again. Three cities late, 2 bars, 3 restaurants? Oh my god. Sounds like a nice night. Did you accelerate between the cities or move at a constant velocity? And have you considered, while accelerating, taking your shoes off and hanging them by the shoelace to observe how they behave? Stuck at a drawbridge? Oh god. Okay, so the entire city is like effed? Oh no. This is the plane. It's accelerating. Not 2, just 1 shoelace. Isn't... Okay, I'm just imagining, like, when you accelerate forward, you get pushed back into your chair because of inertia. I might be on the wrong tangent here, but is it gonna swing like that way? But it's actually like pulling the shoe along that way. Accelerate. I don't know. That just felt right. 2 bars and 3 restaurants, should all be hanging out with Phobos more? Dude, seriously. Absolutely insane. What? It's just a normal X and Y axis. There's nothing wrong with this. I don't see a single thing wrong. Should the net force be 0 or non-zero? It has to be accelerating, right? Because it's on the plane. So I think it's a non-zero answer. You always say positive Z. When I was a kid, I would always say the ceiling or the sky, depending if you're inside or outside. I feel like it should be backwards. I don't have the physics justification for it, but I can't get the image out of my head of when you're accelerating forward, you get pushed back in your chair. Negative X. Yep, I'm just gonna draw a normal three-dimensional coordinate plane. X, Y, and Z. I haven't marked a final answer yet. I'm saying it should be a non-zero force because it is accelerating with the plane. I was saying. Oh wait. Is it 0? No, it's. Fuck it. I'm saying E. It has mass and it is accelerating, so it should be a non-zero force. And just intuitive about what happens when you accelerate, you go backwards. You're saying E2? Okay, thank you. As like Regigigas. I didn't do that thing, so we've been talking about who wants to be a millionaire for the last like hour or two, but I remember my friend, like, I think he got it from the internet, but he was telling me some crazy like Pokemon theory about how like you go to one of the Reggie's caves and like you do a certain thing and then like a unicorn comes like running out and like all this crazy stuff happens. I don't remember. It was like one of those Pokemon legends, like Mew is under the truck. And it's on point this question too, and I'm too old for Pokemon. I grew up on third gen. I did go back and play 1 and 2. I also played the 4th gen, and then I dipped. What was it like as an adult when Pokemon first came out? Let's should we check our answers up until this point? Okay, B, B, E, C. B, B, E, C. A. A. Okay. And then for 4.6 is the last one, I'm saying E. E. Okay, it is E. Pendulum is accelerating forward, as is everything else in the plane. So there must be a forward net force on it. The pendulum hangs downward and backward. Tension force of the pendulum's mass is upward and forward. But how do you know it's downward and backward? Are you supposed to just know that because you're a human and you've accelerated before? The upward component cancels the gravitational force. That's what causes the forward. Because ropes can't push. You want to make a push rope joke? No, I mean, and on this stream, I don't care about sex jokes. I'm not a family friendly stream, but ropes can't push, they pull. Oh, okay, you're saying that it can't be forwards because that would be pushing? I guess so. I'm really scared of scrolling down because I don't want to spoil. Okay, I'm not scrolling any farther. That's a long remark. Pendul's mass is M. No reason I'm true. Oh, okay. You can use this fact to figure out what your acceleration is by measuring the angle. That's kind of... Dude, this second paragraph is getting crazy. He is flying upward. What the hell? Wow, that's kind of... Whereas doing some hanging shoe experience in various aircrafts. You know what, Cook? You should consider yourself lucky I didn't draw the diagram like that. What even is gravity anyway? All right, we'll wrap up with number 7, I think. When you stand at rest on the floor, you exert a downward normal force. Does this force cause the Earth to accelerate in the downward direction? Only if you're Chuck Norris. I think the answer is yes, but you don't notice it. I feel like I learned that in like high school. One would say the net force is 0. Forward component of the tension canceled out the back. Fictitious force and accelerating frame of reference. Okay, I saw this chapter called Fictitious Forces, and that confused me. Like, that's a weird name. I mean, the remarks kind of covered that relativity bit. All you could make the argument that something should have been addressed to deal with that in the actual question, but I think the second paragraph kind of talks a little bit about how that does come up in this question. Yeah, excellent reference to chapter 12, so we're getting ahead of ourselves here. Want to get your mind blown? Sure. Gravity is not a force. Oh, I've heard it's actually because of the curvature of space-time or something. Like, it's actually like things falling into each other because like space itself gets bent. and that the more mass something has, the slower time goes by that thing. Oh, maybe I'm going the wrong direction with this. De Niro and Clooney are all in for Kamala. 500% match. Okay. Will you stop texting me, politicians? How many do I have to mark as spam? That's how you pronounce it, isn't it? I don't know. It's a fictitious force we experience by always being an accelerating reference frame. G is an acceleration. A ball that appears falling to us is actually at rest. We are accelerating upwards all the time. I guess I've heard, like, Kamala. I don't know. I've heard Kamala. PDD party celebs. Oh, yeah. Ugh. A ball that appears falling to us is actually at rest. We are accelerating upwards all the time. I can't handle two blocks being pulled along by a rope. Her OnlyFans impersonator, you know? I'm sure that exists. Oh, Cam, I get the pun you're making, Cam. I'm pretty sure, like, I listen to some politics podcasts, and that's how they pronounce it. Fucks. Remember to vote, unless you're voting for the person I don't like. I respect it. Is this a safe space for Trump supporters? It's a safe space to... I shouldn't have brought up politics. I shouldn't have read that text out loud, but... Yeah, Penn's over here in the clear. I do like talking about politics. I just don't like talking about politics on Twitch. No. I don't care that you said it, Fembox. I'm the one who mentioned politics in the first place. Ban Fembox? No. American politics is my Super Bowl? Oh my god, Pen. Yeah, that would feel good. No. Okay, in seriousness, I don't care who people... Anyone who watches the stream can support whoever they want to support. I shouldn't bring up politics in the first place because I don't want anyone to feel isolated for their beliefs, at least for the purpose of this stream. You're so right, Pen. I mean, if you actually talk to other people in other countries, things aren't just all like hunky-dory either. America just gets a lot more news articles pushed around the world. Although we are going through an especially, like, you know, turbulent time, but I don't like the whole grass is always greener thing. Or it always feels like the grass is always greener. Yeah, no, I get that feeling too, Fembox, but I also don't like lusting after other countries like they're doing everything better and America isn't doing a single thing right. It's somewhere in the middle. Oh god, Cook, I'm definitely not going there. That's probably the worst thing that you can go to on Twitch. McDonald's and garbage. He did do both those things, Pen, you're right. Alright, I'm doing this last physics problem, and that's the end of the stream, especially because we're getting into the politics, apparently. So you don't notice the motion. No, because unreal force isn't a real force. You're also pulling the Earth gravitationally. No, because there's also friction at your feet. The gravitational thing is interesting. I don't imagine that's it. I think it's A. I peaked my mic. I'm sorry. I need to look at my mic settings again. I feel like I learned in high school that it's A, and I don't want to. If I have another thing that I saw in high school turn out to be wrong, then I don't know what I'm gonna do. It's not A. Ugh. Does the ground actually just like compress like a spring? I feel like they're talking about that. If you're at rest, how's acceleration non-zero? Is it? Maybe it is B. Maybe it's not B. I don't know. Normal force is in real force because you're also pulling the ground. I don't know. I don't see an option for the ground compressing like a spring. Well, the Earth is both pulling me down because of gravity and pushing me up because of the normal force. Is it D? That just felt too advanced. Okay, I guess it is D. I felt like they just hadn't like talked about something that advanced. I don't know. I want to see what how they explain that for number 7. It is D. Okay, I'm not scrolling any more down. Boom, 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 boom. You don't accelerate. That feels that you in italics feels very accusatory. Like, I'm sorry, I'm not accelerating. All right. Is the market essentially your argument? Okay. Okay, I think that's gotta be it. Save me from this politics talk. All right, let's cut the YouTube stream off here. So anyways, here on YouTube, I appreciate you all. Back on YouTube on Tuesday.